Welcome to Ask and Learn.
Okay, so this problem is about a copper cube that is heated and the question asks a few things about energy, and I think the crux of the problem is found in part E, where they say, is there any difference between the specific heat capacity of constant pressure and constant volume? So we kind of want to move towards addressing that question. So the first one asks, let's see, the increase in volume of the cube as you heat it from 20 degrees C to 90 C. So you just want to use the equation delta V is beta times the initial volume times the change in temperature. So for change in temperature, I used that one's going to be 70 Kelvin, so 90 degrees C minus 20 degrees C, and converting to Kelvin from Celsius is additive. So you add 273. So the differences in Celsius are the differences in Kelvin. So yeah, I'll just note that that's 70 Kelvin. The rest of the values are found here. Oh, and I'll use consistent notation. So that's V naught. And then beta is what I found from the table online. So your delta V, using all those numbers, I calculated that it was 2.85, excuse me, I think it was 286 times 10 to the minus 8 meters cubed. So obviously, like, that's really, really small, but that's okay. The cube was pretty small. It was 0.02 meters. I think it was 2 centimeters. I'm just going to double check that number. Yes, 2 centimeters. And so, yeah. So there's its delta V. And then part B, they ask mechanical work done by the cube to expand against the pressure of the air. So you just want to figure out the work done at this constant pressure by the cube. So that's just going to be P delta V, and then P is atmospheric. I'll go ahead and put that in our little chart of givens, or at least I'll put it next to it. Oops, not minus. 10 to the 5 pascals. What a large number. So yeah, so if you multiply this delta V, 285 10 to the minus 8 times 101 10 to the 5, maybe you'll get what I got, which is 0.0029 joules. So kind of makes sense. Like, it's not like the fact that you're heating the cube is really gonna, I don't know, do a lot to the air. So that's pretty small, and I think that'll be kind of key to getting at the crux of the problem. So the next one is the amount of heat added to the cube. So you just want to use, I think this is from an older chapter. Q is, C, and then I guess it's at a constant pressure, because the air outside the cube is constant, delta T. So we don't have the mass of the cube, unfortunately, but we do have its density. So if you use density as mass over volume, and then you get mass equals volume times rho, then you can get that you can plug in for mass as rho v. And then use Cp delta T. So I looked up this Cp. I don't think it actually specified that it was at a constant pressure, which is kind of, the crux of the problem. But I just looked it up from the book. And I had to use the density of copper. And let me just double check what I got for that. It was 8960. So I'll go ahead and put that on my sort of ingredients list. 8960. Kilograms per meter cubed. And yeah, so if you use that row and then you use this, and you use the volume of 0.002 cubed, or you can use that plus the 2.85 times 10 to the minus 8, but it won't make a big difference. So I think either number would work. But I'm just going to put V naught for 30. And then C is what I used here, this 390. And I guess I'm not going to leave that. I'm not going to put a P there, because it should be valid both, which is kind of a plot spoiler. Okay, and then delta T, that's our 70 kelvins. Great. So then if you plug all that into a calculator, maybe you'll get what I got, which is 1957 joules. And so let's compare these numbers. So so if we're thinking about the change, like an internal energy of the system, it's and we know that that's kind of right on the side here, delta U equals Q plus the work done on a system. We can see that it's kind of really dominated by this Q term because this work is pretty small. And then I guess it's losing energy because it's doing work. So I'll call this work by, where work by equals minus work on. And then I guess I'll just write that just in case that gets confusing. Work by equals negative work on. Okay, so now to part D. And then they want the change in internal energy. Right. So that delta U equals, this pen, Q minus the work by the gas. So it's just basically 1957 because I didn't really have not really enough sig figs to determine it. So anyway, I'll go with that. And then for part E, it asks, is it the same? So let's think about it. So in terms of, I'm going to point out specifically what it asks. Based on your result, is there any substantial difference between specific heats at constant pressure and specific heats at constant volumes for copper under these conditions? And so you would use, so to get Q, right, in general, you would use M times C delta T. And then this, whether you not use CP or CV depends on the kind of conditions of the heat exchange. And so, but if we kind of rewrite this in a different way, we say Q equals delta U minus the work done on the gas. We can see that that basically, like, the only difference is between delta U and Q is the work done on the gas, and so there's pretty negligible. And so let's see, I had this argument straight. Let me kind of think through it again. So well, let me just go actually on the next one and then kind of work through it, and probably won't be the most efficient way of thinking about it, but hopefully it still makes sense. Okay, so the goal is to show that, which I think is going to be at least to show that CP is approximately equal to CV for part E. So we know that Q is equal to MC delta T, and it's also equal to U minus W minus the work done on the change in internal energy. And so we know that this term is generally going to be small. And so if you were to calculate the heat, you could do this delta U minus W. And then for a constant pressure, that's what you would do. That's kind of what we did. We said Q is this delta U minus the work done on the system. And if we had neglected if it had been instead of constant volume, we would have just like neglected this term because it's a constant volume. And so we would have just completely neglected that term, and we would have basically gotten like the same answer for the heat for Q using this calculation. Yeah, that's it. And so then if it's always equal to MC delta T, and these are all the same, then you're going to kind of basically have to use the same C in order for this delta U minus, because delta U minus W is basically equal to delta U, because this is the work on the gas is so small. All right.